So this is joint work with Ohad Feldheim, who is sitting here somewhere in the middle, and also Raaz Dwivedi and Aaditya Ramdas. And I never met any, I mean, I met Ohad, who's sitting here, but the other two I didn't meet at all. And this was also the state of affair between me and Raaz in our first and only paper that we wrote together. We wrote it without meeting each other. Just remember this. Okay, so what is this talk about? Let's say that we have xi random variables that are uniform in 0, 1, i.i.d. This is big enough, right? Hopefully. And we look at the empirical measure. Okay, so we look at nu n, which is 1 over n, the sum of delta of xi, I equal 1 to m. Okay, so this is the random measure. And the law of large number tells us that this random sequence converges to the uniform measure on 0, 1. Okay, so law of large numbers, it tells us that this goes to Lebesgue measure, or let's just write it as uniform 0, 1 measure. When I say that it tends to this, what does it mean? It means that the convergence here is almost surely in distribution. Okay, because these are random measures, so the sequence of random measure converges in distribution with probability 1. So this is, I'm just amused by having both kind of convergence put together. Okay, that is not too hard. How fast is this convergence? Well, we can look at, we need to find some measure of distance between this and this. So the measure of distance is the discrepancy. The discrepancy, let's just put these already. Okay, so dn is the discrepancy between nu n and the uniform measure. This is the superroom over all a and b between 0 and 1 of the difference between nu n of the interval ab, okay, like this, and the length of the interval, meaning the uniform measure of the interval, which is just b minus a. Okay, so we go over all interval and we ask ourselves, what is the measure, the empirical measure of this interval, and we look at the difference between this and what we expect, and we take the superroom. So how does this thing behave? Well, it tends to 0, which is just another way of saying that this converges to this. But more than this, we know that dn is roughly 1 over square root of n, and maybe 1 is not correct, so O of 1 over square root of n. So this is basically because if we look at n different points and we look at the difference, so let's pick a equal to 0 and just go over all the b's and go from left to right, from b equals 0 to b equal 1, then this term is roughly a Brownian bridge. It starts from 0 and it ends also at 0, and in between it's Brownian motion, and the right scaling is square root of n. Okay, so the maximum of the Brownian bridge is going to be roughly 1 over square root of n. Okay, more or less. Okay, so this is nice, but can we do something better than 1 over square root of n? So first, let's change the definition of discrepancy slightly. So let's put here, instead of this, let's multiply this by n. So instead of the empirical measure and the uniform measure, we instead look at how many points we expect to fall in this interval, a to b, versus how many points actually fell in this interval. Okay, just n times this, and then this changes to roughly square root of n. Okay, just help with things that looks slightly nicer if you don't have to divide by n all the time. Okay, so what can we do to make the discrepancy lower? So suppose that you have the power of two choices. So what does this mean? It means that each time step, okay, each time, you get 2 points, two i.i.d. uniform 0, 1 points, and you can choose. You can choose which to take, which to use. I don't know. Which is the next xn? So can you do anything better if you have this power of can you make it converge faster? Well, the answer is yes. Okay, so all the theorems are joint with everyone, so I don't bother writing. So there is a strategy. So by strategy, I just mean some rule for how to choose which point between the two to choose. There is a strategy that gives you dn, which is only all of log cubed, which is much smaller than square root of n. Okay, and
strategy is adapted, so you only use the past observations.
Only use the
past observations you don't.
Yes. Okay. Yeah. Of course, by strategy, I don't mean that I have knowledge of the future. I only observe what happened in the past, and.
Instead of course, is there something obvious?
Is it what?
Is the answer obvious?
The strategy?
No, is it obvious when you get to see all the points?
Is it obvious? It's easy, I think. I think that if you just go, again, from, say, left to right, so you have two endpoints, and you want to choose endpoints out of the two ends, so it will minimize the discrepancy, something like that, I guess. So I think that if you just go from left to right and try to make the discrepancy as small as possible for each end, but, adding a point or omitting a point, you will just get something like log n. Okay, you can't get better than log n, so this is, a remark. So lower bound of log n, roughly log n, yeah, I mean theta of log n. This is just because if you look at endpoint or two endpoints on the unit interval, there is some gap of length, of logarithmic length. Okay, not logarithmic. There is some interval as length is log n over n times some constant, some small constant that is empty. There are no points there. So if you choose this interval here, you multiply by n, remember, then you get log n no matter what you do. Okay. I'm not sure what the truth is. I mean, we can probably improve on the 3 here, but not lower than 2. Okay, at least, I mean, the idea that we have, I don't know how to improve it beyond log square. And the lower bound is log, so I'm not sure what the best you can get in this setting.
So if you have all the two endpoints ready, then you're sure that the log n you can get.
If you have, if you know the future, or if you just choose endpoints out of two endpoints, you can still not get anything better than log n.
But you do get log n.
Yeah, you do get log n. It's as I said, I think it's easy. Okay, yeah. Oh, okay. So, yeah. So let me write something more accurate than this. So we have one strategy to rule them all. Okay. So we have a single strategy that will give you that dn over log cubed of n. The supremum of this is finite. Okay. Almost sure. Okay, and in fact, if you look at the lim sup, then I can give you some number here, not just infinity, but some number, some concrete number. It cannot be, very big.
Is the lim sup constant by some 0, 1 law?
is the lim sup according to this strategy? I don't know. I don't know. I guess it will be, but we never tried to prove a lower bound so on the lim sup. So, you know. So this is this answer basically a question or variation of a question by i.i.d. i.i.d. gave some specific strategies to analyze. For example, when you have 2 points, you take the point which is farthest away from all the points that you already chosen, or maybe the point that is in the biggest interval, something like that. And we think that we don't know how to prove this, nobody knows, but we think that these kind of strategies cannot give you anything much better than square root of n, because they're local, we don't believe that you can get an improvement. Okay, our strategy is global. It looks at the entire measure and yeah, that's something. I will show you in a second. Okay, so this is in 1 dimension, and we have the unit interval. What about higher dimension? So higher dimension, we have something on the i.i.d. point on the 0, 1 to the d, uniform, etc. Everything is the same. The discrepancy of a random i.i.d. point sequence is also square root of n. This doesn't change.
Do you use boxes, squares then, or boxes?
I'm sorry?
What do you use? What's the analog of the intervals?
Okay. So what is the analog of the interval? We use boxes. We use rectangle or hyperrectangle, depending on the dimension. Okay. So here the superm will be over all rectangles. When I say rectangles, I mean axis parallel rectangle. Okay. So it might not be, I mean, in some contexts it might be very natural to use this, in others it might not be, okay? So, but that's what we can do. So, suppose that we use this discrepancy, then we have an analog of the same strategy, it's very similar, strategy, that will give you a supermem of dn of log to the power of 2d plus 1. And we'll define it. Okay, so
Sorry, I missed what you said about axis parallel. So you could rotate them?
No, so they're parallel to the axis. if you rotate them by 90 degrees, they're still parallel to the axis, and then it's fine. Yeah. Okay. And just okay, so this is the second theorem, and the proof is very similar, and the strategies are very similar, though there are all kind of small details to check. And we have a conjecture that there is another strategy. Okay, so first, one conjecture is that our analysis of this strategy is not optimal, and it's actually a little bit better than what we did here by roughly a factor of d over 2. I mean, log n to the d over 2. But actually, there is a strategy that seems to work much better, a different one that will change this to d plus 1. Okay, and here we get to the realm of what is the minimal discrepancy that you can actually get from any sequence, not just a sequence that a power of 2 choices. And the truth of the optimal sequence is not known, and there are two bounds, and the upper bound. Okay, so for any sequence. Okay.
So sorry.
Yeah.
So what does this mean?
Okay, so you have a sequence of points in 0, 1 to the d, to the unit interval to the power of d, and you look at the discrepancy for all n. For each n, you get some number, and then you ask what is the upper bound that you get for the sequence. Now, there's a question of whether there exists some n, that such that the discrepancies tend to be bigger than for other n. So it's not. It could be something different for typical n for all n. But anyway, we think. I mean, we know that it's not us. There are upper bound and lower bound. The upper bound is log n to the d. So there are some sequences that are slightly better than what we conjecture this sequence is, but only slightly.
Finite sequence here.
No, infinite sequence. Infinite sequence, just that this holds for, or if maybe you should write it as, dn over log n to the d is finite. Okay. So there are known sequence.
What are they? There exists a sequence.
Yeah, there exists a sequence like this. Okay, and there are. Yeah, I wrote it in a sequence. Okay, sorry. So there exists a sequence like this, and it's also known that for any sequence, we have that dn is at least log n to the power of d plus 1 over 2. Okay. You have to be slightly careful here because it depends on whether you look at each n separately or in the entire sequence, right? If you take a specific n, then, and let's say the dimension is 1, then obviously you just take, regular interval of 1 over n plus 1. Okay, 1 over n, doesn't matter. And then you get a discrepancy that is just 1 over n or constant after we normalize it. Okay, but if you want it to work for all n at the same time, then you can't do this, and at least there exist infinitely many n such that this inequality holds. Okay. Yes?
So in higher dimensions, you are taking supreme rectangles or like cubes?
In higher dimension, you look at rectangles. Okay, so, and as I said, x is parallel rectangle. So rectangle like this, or like this, or like this.
So are there results which say that if you, instead of taking cubes, if you kind of, it's not
no, so we don't allow rotations. We just look at axis parallel rectangle. Okay. Okay, and one last, one more remark. I said here power of 2 choices, meaning you get 2 points, but in fact, we don't need that much power. We are fine with only being shown 1 point. Okay, so you get 1 point and you choose whether to keep it or whether to throw it away and take another uniform point, which you don't know what it is, and you get the exact same result. I mean, the strategy is of this form. And in fact, if we don't care about the constant, if we just want this to be finite or this to be finite, then we can do it with what we call 1 plus beta thinning, meaning that only with probability beta you get you are shown a point and may choose to discard it, and otherwise you just get a point and you have no control. Okay, and it just changes the constant which bound this here. Okay. When did I start and when do I have to finish?
Half past.
Half past. Okay, I'm fine then. Okay, so let me give you a little bit of background on where this power of 2 choices come from. But it might not be, maybe that not everyone is familiar with this. So the classic setting is the balls and beans. Balls and beans mean that you have n balls and you throw them randomly into n beans. And balls, uniformly i.i.d. Put in n beans. Okay, so in that setting, in each bean you have roughly a Poisson 1. Okay, so for each bean, is roughly Poisson 1, number of bars, right? And then if you want to look at which bin is the most loaded of the n bins, you just have to, I mean, they're, again, roughly independent. This can all be formalized. And then you take the maximum of n independent Poisson 1 random variables, you get the maximal load. Max load is log n over log n. Okay, this is all well known. So there is a classical result of Azar, Broder, Karlin, and Upval. If we take two choices, and you take the bin, I mean, you are offered two bins, and you have to choose whether to put the ball here or here. You take the bin that is less loaded, then instead of log over log log, you just log log. Okay, so this is, in a sense, it is an exponential improvement, right, in the right scale. A big improvement, and people actually use this for server loading and stuff like that.
But this is a very local strategy as well. So why did you say that you think that the local strategy won't work?
Right. This is local, but the discrepancy that we measure here is also local. You just look at one bin and ask what is the load in one bin. And here, instead, we look at an interval. So if we would put this in the discrete setting, we would have to look at an interval of bins. Like take all the bins between the K and the L bin and ask what is the difference between how many bars are there and how many you expect to be there. I mean, in the uniform distribution. And then you will not get such a good improvement. Okay, if you did, then this would be very easy. Okay, thank you for the for the question. Okay, so as I said, this is like from 95 or so, and i.i.d came with the question of what to do in the discrepancy setting in the power of two choices, and I just want to add one thing. There's a whole history, but I want to talk more about the proof. There's a whole history of point processes and interval subdivision processes. For example, there is a Kakutani process, which means that we have a few points on the interval, and then we choose the largest interval and put a point there. Okay, uniform point in the largest interval. And this seems, I mean, again, it seems like it would make some big improvement in the discrepancy, but it doesn't. It only gives you an improvement by a factor of 2. Okay, so it's still square root of n, and it's not surprising because again it is local, so it falls under conjecture. Okay, so one last remark. Why is that? I don't usually do this, but why is this useful? So you might think of the following setting. Maybe you want to calculate some function. You want to calculate the integral of some function on 0, 1 to the d. And so one way to do this would be to use Monte Carlo, to use the random point. And then if you want to get better convergence to the value of the integral, you want this point to be as nicely spread as possible. So some people actually use low discrepancy sequences, like I said here. But sometimes you either don't want to use this because you suspect somehow that the function might behave badly on a sequence like this, or maybe you are not free to choose the point. I mean, maybe you get random point, okay, and you want to get lower discrepancy from the random point that you get, and you just want to discard some of the points and hopefully as few of the points as possible and reduce the discrepancy. Okay, so that was just a small remark. Let's talk about the proof. Okay, so if I have to say, to give you the idea of the proof in just one word, then the word would be har. Okay. By har, I mean the har function or har basis, har orthogonal basis. But I have some more time, so I will actually use more words than this. So what are the har functions? Okay, so let's add this on one dimension, and then I'll say a few things about more dimension. So the har function are just the function that I'll just draw them, and then it will be much clearer, I think. So maybe I'll just draw them all in the same. I have a few colors. So the zero order har function is just 1 on the entire unit interval. The first order har function is 1 here and minus 1 here. The second order are 1 here and minus 1 here, and 0 otherwise. And another one is 0 here, 1 here, and minus 1 here. Okay, maybe I'll draw them separately. Okay, so this is order 0. Okay, let's remove all these. This is order 0. This is order 1. This is order 2. This is also order 2. 1, 0 here, 1 here, and minus 1 here. Okay, etc., etc. You take a dyadic interval. You choose a dyadic interval, and in the left half it's 1, and on the second half it's and the right half it's minus 1, and the rest is 0. Okay. Yeah.
Is this the same as the Rademacher basis, or is that?
This is what?
Rademacher functions? No. Rademacher functions or Rademacher?
I don't think so. I don't remember what Rademacher functions are, so.
Locally,
The Rademacher functions are never zero. No. They're like the waves, like the cosine wave, discretized to 1 minus 1. And this is 0 on most of the intervals.
So Rademacher is what I call Walsh? Yes, okay. Now I know what Rademacher.
These are the functions that come in the Levy construction.
Okay, so anyway, is it okay? Yeah. Okay, so the idea is that we look at our empirical measure nu n, and then we want to look at the dot product, the scalar product between nu n and age. Age is one of these functions. So this is just equal. Maybe I should write it. This is just equal to the 1 over n, the sum of age xi. Okay, xi are those the point that consists of this empirical measure. Okay, which again amount to just looking at how many points fall in the left half versus how many points fall in the right half of this dyadic interval represented by h. And the idea is that we want to choose the next point, to make the next point, so that this quantity will be biased towards 0. Okay, we give it some push towards 0, and we want to do it for many ages simultaneously. Okay, so this is a very high level explanation. Okay, so in order to do that, let's look at what kind of distribution can we actually implement by using this power of 2 choices, or more precisely by using the power of 1 thinning, or 2 thinning, sorry. Okay, meaning that you get a point and you have to choose whether to take it or not. So here's a lemma. If you have some function g, which is a probability distribution function on 0, 1, okay, and the density, probability density function, okay, so this is density. Sorry. And we know that G is between half and 3/2. Okay. Then there is some strategy that gives us giving G as an output. Okay, meaning there is some strategy for me to whether to accept or reject the first point that I get, so that the output point will have exactly this distribution. Now, this is not if and only if. This is not equivalent. This is slightly weaker notion of what you can do. Okay, what is the proof? The proof is reject or thin reject with probability that is 3/2 minus G. Okay. So if you are given X, this is the probability for which you choose to get a new point, and otherwise you get this point. You take this point. What is the probability of rejection? I mean, overall probability of rejection. This is just the integral of this thing, right? So the integral of 3/2 minus G, and this is just half. Right, because it's 3/2 and G is a density function. Right, and what is the probability of getting exactly X? I mean, it's not a probability because this is continuous, but still, okay, the probability of getting X, so let's call it big X equals little x. So this probability is the probability that we get X to begin with. Okay, so probability of X times the probability of not rejecting. Okay, so not rejecting is 1 minus this, right? So this is just G minus G of X minus half. Okay, plus the probability of not getting X times half, because this is the probability, the overall probability that we rejected and we got a new uniform point, right? With probability half we rejected, and then I'm sorry, I wrote 1 minus P of X. Sorry, so it has to be half times P of X, okay, which is equal to G of X. Okay, so you have to look at the probability near delta X and delta X here, and here you have delta X. Okay, we take some small intervals. Suppose that the G doesn't change on this small interval. The probability that you get a point here times the probability you didn't reject it plus half the total probability you rejected times the probability of this interval. Okay, you get exactly G. Okay, so you have a lot of flexibility in what you can do. So now we want to use this flexibility, and did I see? And our strategy will be to look at our G. Okay, G of X is going to be this 1 minus, and I leave here something empty. I will fill this in a minute. Take the sum over all her function, okay, ages that belong to h log n, and h log n, so let's put it here, hk. These are the her function of order at most k. Okay, so the order 2 to the minus k is the size of the dyadic interval, and k is the order of the function. As I said, this is order 0, this is order 1. Okay, it depends on what you define by the dyadic interval. It doesn't really matter what you choose here. That's just a factor of 2. So we look at all these her function, and you look at the sign of mu n and h. Okay, meaning for each function you choose whether you want to get a bias, in this way or in this way. You always put it in the direction of the 0, which means that we put here minus. Okay, and we take here times h. Okay, so Okay, I didn't put the coefficient here. Okay, I just want to present the idea. The idea is that I look over some function. For each of them, I ask myself, is the distribution, the empirical distribution right now, is it currently biased toward here or toward here? And then I want to push it in the right direction. Okay. Now, in order for this to satisfy this condition, what we have to put here is just 1 over 2 times log n. Why is that? Well, the sum here is over all half functions that are of order at most log n. We got plenty of these, but for each point, only one function of each order is non-zero, right? I mean, let's just look at order 2. Here, this one is non-zero here, and this one is non-zero here. And the same for any other order. So the sum here is at most log n many function, and each of them is bounded by 1. So you have to divide this and half to get a half from there. So we can actually achieve this distribution, the distribution with this density. Okay, what happens when we use this G? Well, let's take a look at.
So, Ori, can you say, so that's right thing? Can you say that is it true that that's an approximation of your current distribution in the basis up to log n? What you write on the right hand side, is that true?
It's not. I mean, it's not an approximation in the sense that it's not like taking, discretizing the distribution and just asking how many points are there in each small cell. Okay, it's a kind of an approximation, but I'm not sure exactly in which sense. Okay. Yeah, it also, of course, depends on which K you look at. Okay, so here I have to be at least slightly careful. I kind of assume that here n is fixed. I'm giving a strategy for a fixed n, and for the real strategy, what we need to do is change n. In fact, this is the same strategy. Just change n, along with the sequence. Okay, but it's easier to see what happens when n is fixed.
If the h were if the mu n were normalized and you didn't put sign, right? Then it would just be the projection to that space.
I didn't put sign. This is the sign of this, right?
Okay. Mu times h without the sign would be a projection.
Yeah, right. Okay. If we didn't put this, then this would be just a projection over the space of. I have to think for a moment what is the space. But basically, I think it will be just counting for each cell of size 2 to the minus log n, counting how many points there are in this cell, I think.
The functions which are piecewise constant on the Aaditya.
Yeah. Yeah, I think that the value of the function will be just averaging over each of these little cells. Okay, but we don't do that. Okay, so we want to put we use the sign here. Okay, yeah.
Ori, so just to be clear, so you said you fix n, that is you're gonna give me n points altogether.
Right.
But
So
then the n that appears in this guy, this is gk.
you're right. So this is actually the strategy that we use at the end stage, and this changes. Okay, the coefficient here changes, and also the sum here over which function you do it also changes.
But most importantly, mu n is the current situation.
Of course.
Yes.
Yeah, of course. This is what happened for the next point. But it's easier to see that everything works if you think of n as fixed and you just choose, you choose this n. This is, let's say, be capital N. Okay, and this will say little n, and little n goes from 1 to capital N. Okay, and then the sum is over a fixed set, and the base is fixed, so it's nicer. Okay, so let's see let's look at. Okay, just one remark. So this strategy means, that if you apply the lemma, right, that you want to reject with probability that is 3/2 minus of this, right? So the probability of rejection is half plus this thing. Okay, just remember this. Okay, let's look at nu n times the dot product of nu n and age for any age that falls in this set. Okay, so the thing is, if we look at this distribution and we look at what we're doing in the next stage, okay, and we want to see how it affects. So we want to look at let's say the expectation of what happened in the next stage. Let's say given what we have now, okay, so minus nu n age. Okay, so this is going to be always in the right direction because all the other half functions are orthogonal to this one. Okay, maybe we'll give it a special name, so let's make it age prime. Okay, all the other half functions that we use are orthogonal. So when we take the dot product of this, okay, of this distribution with this age prime, what we get is exactly the sign of, so let's say the sign of nu n and age prime over 2 log n. Okay, and probably minus again. Okay, so we get exactly bias in the right direction. Okay, let's put it in word instead of this. If we look at the interval and then we see, okay, we have more point here than I have here. Okay, then now I tend to put a point here. By how much I tend to put more a point here? By roughly 1 over 2 log n. Okay, the difference between the probability of putting a point here and here is going to be this. So this gives us a bias of this strength, and this is true for any of the ages that belong here. So this means that you have typically this thing age nu n and age. This is going to be roughly log n, and you have many of these ages. You have polynomially. I mean, age log n is the size of it is polynomially big in n. So we expect that the worst one at time n will be log n more. We're going to be worse by a factor of log n. So we get another log n here, and here, and I don't really have too much time left. So the thing is this final to claim. If we look at the dyadic interval, okay, so dyadic interval is a convex combination of nu n and h. Meaning, let's demonstrate instead of proving. Suppose that we want to know how many points do we have here at the end. If we know how many points we have, let's say, more in the second half versus the first half, we have to take the entire point that we have, which is n, we divide it by 2, so we have n over 2. And we also need to divide the difference between them by 2. So here we have, so if we know how many we have more here than here, we can calculate how many we have here. If we know how many more we have here than here, we can calculate, of course, how many there are here. If we do the calculation, we see that calculating this gives us not just a combination, but actually a convex combination of these. So meaning that if we know that all of these are only log square, then we know that for any dyadic interval, we have at most log square n point more or less than what we expect to have. And finally, any interval can be decomposed into at most log n number of dyadic intervals. Okay? So if we have an interval, let's say instead of this is 1/4 and 1/2, if we take something like this, then we can write this as the sum of dyadic interval, and here the sum is over logarithmically many dyadic intervals. So we get from this, we get another factor of log n. Okay, so the number of points differs by log cube. Okay. Okay, so we have one log is from the bias, that is only 1 over log. 1 log is from the number of Haar function that we have, and 1 log is to get an arbitrary interval. Okay, decomposed into the adic interval, we need another log. When I say you need another log, I mean that the error between the interval that we want will be polynomially small, okay, which you don't care about polynomially small. So we have 3 factors of log. 2 of these, in higher dimension, they turn into log to the d, but we suspect that we can actually get it slightly better. One last remark, I promise just 1 minute. So here we said that the rejection, this gives us a strategy which says, okay, reject with probability half plus this thing. Okay, what is our conjecture? I already deleted it, but we said that we have a conjectured strategy that we think that gives us log to the power of d plus 1, gives us something much better. Well, the strategy is simply to look at this sum, which just means to look at the basically just at the majority of the signs. And if the majority of the signs are pluses, then we reject. If the majority of the signs are minuses, then we accept. And if it's exactly equal, then we just do it with probability half. Okay, so we want to basically want the bias here to be as big as possible. The problem is that we don't know how to analyze this strategy, but simulation showed that it's much better than using this strategy, and it more or less looks like log to the d plus 1, but it's kind of hard to actually give, to actually convince ourselves that this is exactly it. Maybe it's even better. Maybe we can get something better than the best known sequences. Okay, that's it.